In this lesson, we're going to continue our exploration of stereochemistry, taking a look at chirality and chiral centers. Chirality is a property of an object in which its mirror image is unique from itself. The classic example is a hand, right? If you take your right hand and put it in a mirror, what do you see? You don't see a right hand, you actually see a left hand. The right and left hands are chiral. Each one has a mirror image that is unique from itself. Here I've got a molecule that is chiral. You can see that this simple little one carbon molecule and its mirror image are not the same as one another, right? You can't superimpose them on one another, so they're not the same. They have different spatial arrangements, even though the atoms are connected the same way. Now, chirality is caused by an absence of a symmetry element, typically something like a mirror plane. And a mirror plane is just an imaginary plane that bisects an object such that one half of that object reflects exactly to the other half. So in these two examples, you can see that each compound has a mirror plane that perfectly bisects the molecule so that one half completely and perfectly reflects to the other half. Because these two compounds have a mirror plane, that means that they are achiral. That is to say that their mirror images would be the exact same as themselves. If you look at that first example above, there is no mirror plane. There is no way you can bisect that molecule such that one half perfectly reflects to the other half. And since it lacks that symmetry element, it's chiral. It has a mirror image that is unique from itself. Now, in organic chemistry, chirality is usually found in molecules that possess a chiral center. A chiral center is a tetrahedral atom that has 4 unique substituents attached to it. So if you look at the model here, we have a chiral molecule, and that carbon is a chiral center because it is a tetrahedral atom, it's sp3 hybridized, and it has 4 different groups attached to it, right? A white group, an orange group, a green group, and a purple group. So that carbon is a chiral center. However, when you're looking at the actual groups involved, you have to be holistic. You have to consider the entire group, not just the first atom bonded in each group. Let's look at a much more complicated example. Here we've got this ring structure. Now this molecule has 12 non-hydrogens on it. Think about it, hydrogen can never be a chiral center, right? It can't be sp3 hybridized and it can't have 4 different groups attached to it. But all these carbons and that bromine and that oxygen, well, potentially could. Now for SMART, we can immediately exclude a number of these atoms from being potential chiral centers. Remember, we need an sp3 atom and it has to have 4 unique groups attached to it. So for example, the oxygen, it actually is sp3 hybridized, but it only has 2 things attached to it, right? Hydrogen and a carbon, and those groups may be different, but it's only 2 groups, so it can't be a chiral center. Same thing with the bromine. The bromine is only bonded to one thing, so of course it can't have 4 different groups attached to it. So those atoms are out. Now, all these carbons that are a part of a methyl group, those carbons can't be chiral centers either, right? Because a methyl group has 3 hydrogens attached to a carbon, and hydrogen is hydrogen. So those carbons can't have 4 different groups attached if 3 of the groups are the same. So if you ever see a methyl carbon, yeah, it can't be a chiral center. The same thing is going to be true for a methylene. A methylene is really not a group, it's more of a subgroup. Methylene just means CH2. And of course CH2 has to go on to 2 other things, so it's not really a full group. But we use the term methylene a lot in organic chemistry. And if you look at the structure, there are actually a couple of methylenes, right? At the very bottom, that carbon is bonded to 2 hydrogens. And again, it can't be a chiral center if it has 2 identical groups attached to it. It needs 4 unique groups. So that carbon is out. And then there's another methylene over here. Again, because it has 2 hydrogens, it can't have 4 different groups attached, so it's out. So that really only leaves us with 4 atoms to consider. We've eliminated 8 of these other atoms as potential chiral centers. So let's work our way around the ring. Let's start at the top carbon of the ring. Is that a chiral center? Well, it is sp3 hybridized, so it is tetrahedral. Does it have 4 different groups attached to it? Well, if you look at it the wrong way, you're going to say no. You're going to say, oh, it has an oxygen attached to it, and then it has 3 carbons. But a carbon is not a group, right? A carbon is an atom. You have to be holistic when considering the actual groups and whether or not they're unique. In other words, this carbon is attached to an OH, a CH3, and then this left half of the ring, and then this right half of the ring. And those 4 groups are unique, right? You can't say that a methyl group is the same as half of this ring. And you can't even say that half of this ring, the left half, is the same as the right half. So that carbon is sp3 hybridized, and it has 4 unique groups attached to it. So it is a chiral center. Moving clockwise to the next carbon. Is this a chiral center? Well, it's again sp3, and yeah, it actually has 4 different groups attached to it. So that carbon is bonded to a methyl group, then it goes on to this top half of the ring, and then to this lower half of the ring, which is definitely distinct from the top half. And then don't forget there's a hydrogen implied there by the skeletal structure, right? And that's 4 different groups. So this is also a chiral center. Working our way again clockwise, we go to this carbon, and you can probably pretty quickly see this is not going to be a chiral center. It is an sp3 tetrahedral atom, but we can immediately see that it has 2 identical methyl groups attached to it. So that means it can't have 4 different groups, so it's not a chiral center. We already omitted this next carbon, right? That was one of the methylenes, so we can work right past that. Going clockwise again, taking a look at this carbon, we can see that it has a bromine attached to it. Then it has this upper part of the ring, this lower part of the ring, and a hydrogen. And again, be very careful, right? It's very tempting to say, oh, this carbon goes on to this CH2 above it and this CH2 kind of below and to the right. But a CH2 is not a group. It's not an entire group. It's a subgroup. A CH2 has to go on to more stuff. And if you go past the CH2 above it, it goes on to different stuff than the CH2 below goes on to. In other words, those are 2 different groups, right? This top half of the ring does not look like the bottom half of the ring. So those are different groups. So yes, this is a chiral center. It has a bromine, a hydrogen, this unique top half of the ring, and this unique bottom half of the ring. And then again, we've already omitted this methylene here. So it turns out that this molecule has 3 chiral centers. Now, the specific spatial arrangement of a chiral center can be represented in 2 dimensions a variety of different ways, and we're going to look at 2 of them. The most common is a dash wedge projection, also called a perspective formula. I've also even heard it called a Nada projection. It uses a dash and a wedge and 2 straight lines attached to the chiral center. So if you look at this example, I have it represented both as a dash wedge projection and as a 3D model. And you can see from the 3D model that this is a chiral center, right? We have this carbon with 4 unique groups attached to it, and it is tetrahedral. To represent the actual spatial arrangement, the 3D arrangement of all of those groups, we use a dash and a wedge. Here's how it works. The 2 plane lines represent atoms that are in the plane of the drawing itself. So if you look, the bond to the chlorine and the bond to the iodine are on straight lines. And if you look at the 3D model, that's exactly what we see. Those atoms and the bonds to them are kind of in the same plane. If you look, the hydrogen atom is kind of tucked away behind the carbon, right? It's sort of hidden. It's fading back away from us. And so we represent that with a dash. And then the orange bromine atom, you see how it's coming out at us in the model? We represent that coming out with a wedge. You can see that in the perspective drawing, we have the bromine on a wedge. Whenever you're using dash wedge projections, it is really important to remember, always have the dash and the wedge together. Don't let them get separated by one of the plane lines. That actually means that the atom is not tetrahedral. So always keep the dash and the wedge kind of paired together. Another way that organic chemists represent the actual spatial arrangement of a chiral center is using a Fisher projection. So here's a Fisher projection. What this is representing is the same shape as this 3D model. You can see that in this model, looking at it kind of head on like this, we have 2 groups, the horizontal groups, that are kind of coming out at us. And then we have 2 other groups, the vertical aligned groups, which are kind of fading back a little bit. And that's exactly what a Fisher projection does. The bonds represented horizontally are implied to be coming out towards us a little bit, and the bonds drawn vertically are fading back a little bit. In other words, it really looks like this, with 2 dashes in the vertical positions and 2 wedges in the horizontal positions. Now, we'd never draw it that way, but a Fisher projection is an alternative way of representing the exact 3D nature of a chiral center. So any chiral center can exist in either of 2 spatial arrangements. Again, it's kind of like those hands, right? A hand is simply a thumb, an index finger, a middle finger, a ring finger, and a pinky arranged in that order. But you still have 2 unique hands, a right hand and a left hand. They are mirror images of one another. So just like we use the terms right and left to describe which version of a hand we're looking at, we use the terms R and S to describe which version of a chiral center we're looking at. And that's called the configuration of that chiral center. To determine the configuration of a chiral center, we actually use the Cahn-Ingold-Prelog rules, the same rules we use when looking at EZ isomers of alkenes. Here they're applied just a little bit differently. What we do is we look at the chiral center and we look at the 4 groups attached to it. The first atom of each group the atom that is directly bonded to the chiral center. We compare those atoms based on atomic number. So in this example, you can see we have a chiral center with a hydrogen, a chlorine, a bromine, and an iodine. And if we rank those according to atomic number, we would have iodine as 1, bromine as 2, chlorine as 3, and hydrogen as 4. Next, we have to ensure that the 4 group is positioned going back and away from us. In this original example, the 4 group, the hydrogen, is already fading back, right? It's on the dash. But look at this next example, right? If we prioritize the 4 groups here, well, it's the same groups we had up above. So we have the iodine 1, the bromine 2, the chlorine 3, and the hydrogen 4. But what we see is that that 4 group, the hydrogen, is not going back. It's actually on a straight line. Now, when we determine the configuration of a chiral center, we have to make sure we're looking at the molecule with the 4 group directed back. That means that we need to manipulate this drawing such that the 4 group is positioned back, and we need to do it without disturbing the spatial arrangements of those groups. So there are a few ways you can do this, but I'm going to show you the way I like to do it. Here I've got a dash wedge projection of a similar molecule. It's got the same 4 groups attached to it. What we're going to do is we're going to take this molecule, we're going to hold on to one group so that it doesn't move at all. We're going to hold that group, and we're going to rotate the molecule along the bond between that group and the chiral center. And that means that the other 3 groups that are attached are going to rotate. So if I hold on to the hydrogen, I can rotate the other 3 groups either clockwise or counterclockwise. You see that when I do that, the positions of the lines and the dash and the wedge don't change, just the atoms that occupy those positions. Now when you do this, you should be smart about it. There are a couple of things you want to consider. First of all, don't hold the 4 group. If you hold the 4 group, it's never going to move into the back position. It's not technically wrong, you're still going to create perfectly valid drawings. It's just that you're not going to create a drawing where the 4 group is going back, and that's what we need to do. The other thing you shouldn't do is to hold the dashed group. If you hold the dashed group, the 4 group never has the chance to rotate into that position. Again, it's technically okay to do this. You're going to create perfectly valid drawings, but you're not going to get the drawing you need where the 4 group is positioned back. So going back to our example, what we need to do is hold one of these groups steady and then rotate the other 3. I almost always hold one of the straight lines. So here I'm going to hold the iodine steady. And if I hold that, it's not going to move. I'm going to rotate the other 3 groups. And I need that 4 group, the hydrogen, to rotate into the dash position, currently held by the bromine. And in order to do that, I need to rotate counterclockwise. So if you follow the green arrows, that means that the 4 group, the hydrogen, will rotate into the position of the bromine will then rotate into the position of the chlorine, and the chlorine will rotate into the position of the hydrogen. Remember, we skip over the iodine because we're holding that, right? That's the axis we're actually rotating along. So when I do that rotation, it places the hydrogen into the dash, the bromine into the wedge, and the chlorine onto the straight line. And now we have it so that the 4 group is positioned back, and that's exactly what we need. So once we have the 4 groups attached to the chiral center prioritized, and we have it rotated so that the 4 group is going back, we simply count 1, 2, 3, ignoring the 4 group, and we see what direction we count. So if you look at this first example, counting 1 to 2 to 3, that's clockwise. And if it goes up 1, 2, 3 going clockwise, then the configuration is R. If you look at the second example, we count 1, 2, 3, again ignoring 4. Counting 1, 2, 3, it goes counterclockwise, and if it's counterclockwise, then the configuration is S. R and S stand for rectus and sinister, which are just Latin for right and left. Think about if you're driving a car. If you turn your steering wheel clockwise, the car goes to the right. If you turn your steering wheel counterclockwise, the car goes to the left. So it's pretty easy to remember. Let's take a look at one more example that requires a little bit of a deeper recursion of the Cahn-Ingold-Prelog rules. So look at this alcohol. We can see that that carbon with the dash and the wedge is a chiral center. And by the way, don't just see a dash and a wedge and immediately think it's a chiral center. You can draw methane with dashes and wedges, right? That just shows spatial arrangement. It doesn't necessarily mean there's a chiral center there. But yes, this is a chiral center. We can see that because the carbon is tetrahedral and it has 4 unique groups attached to it: a hydrogen, a hydroxy group, a methyl group, and an ethyl group. If we prioritize those 4 groups, we can see that the oxygen of the hydroxy group is going to be the highest priority, and the hydrogen is going to be the 4 priority. But those 2 alkyl groups, the first atom in each case is a carbon, and that's a tie, right? So remember, what we do when we have a tie, when we have the same element bonded twice, is we look at all the atoms directly bonded to those atoms. So on the left side, that methyl carbon, that carbon is bonded to 3 H's. So we create a list of HHH, and we would order that in terms of decreasing atomic number, but they're all hydrogens. Looking at the first carbon of the ethyl group, that carbon is now bonded to 2 H's and another carbon. So we create a list and we order it again in decreasing order of atomic number, so that would be CHH. And then we simply compare those lists looking for the first difference, and whichever one has the higher atomic number gets the higher priority. So in this case, the very first atom is where the difference is, right? The ethyl group has a carbon in that first slot, and the methyl group has a hydrogen. And since carbon has a higher atomic number, that gets the higher priority. So the ethyl group is 2, and the methyl group is 3. We would then rotate the molecule to make sure that the 4 group is going back. Conveniently, it already is, right? The 4 group in this case is a hydrogen, and it's on a dash, so it's going back. So we don't have to do any 3D rotations. And we simply count 1, 2, 3, and in this case you can see that it goes 1, 2, 3 clockwise, and that means this is the R configuration of that chiral center. Now in these examples I've been using dash wedge projections, but the exact same things would be applied to a 3D model or to a Fisher projection. You prioritize the 4 groups, you then hold one group steady and rotate if necessary to get that 4 group going back, and then you simply ignore the 4 group, count 1, 2, 3. If it's clockwise, it's R, and if it's counterclockwise, it's S.